IBM Simon, a black screen. A phone rings, somewhere in a department store in 1994. It is the size of a brick, and it has a touchscreen, and almost no one in the store understands what they are looking at. The textbook story said the smartphone began in 2007 with a single device, a single keynote, a single moment of revelation on a stage in California. But the evidence for an earlier beginning was buried under 13 years of silence. IBM's device sold only 50,000 units. It had no name people remembered, no culture built around it, no app store, no reason for anyone to believe it mattered. It was filed away as a curiosity, a footnote in trade magazines that nobody kept. In 1992, at a computer trade show in Las Vegas, IBM engineers demonstrated a device they called Simon. It made calls, it sent faxes, it had a calendar, an address book, a notepad, and a screen you touched with your finger instead of a stylus or a button. There was no keyboard, there was no precedent. The press wrote it up as a novelty, a strange hybrid nobody had asked for, and then the story simply moved on. What this changes is the shape of the timeline we tell ourselves. Innovation does not arrive as a single bolt of lightning. It arrives early, fails to find its moment, and waits. The components existed. The vision existed. What was missing was infrastructure. Cellular networks too slow, batteries too heavy, a public not yet trained to want a screen in their pocket. Simon was not wrong. It was simply early, in a world unprepared to receive it. There is something quietly humbling in this. The future does not always announce itself with fanfare. Sometimes it arrives a decade too soon, gets boxed up, and waits for the rest of the world to catch up to an idea that was already finished. The smartphone was not invented twice. It was invented once and forgotten once, before it was remembered. Bell Picturephone. Another device, another decade too early. A black and white screen. Two faces, transmitted live across a phone line in 1964. The technology existed before color television was common in most homes. For decades, the established view held that video calling was a product of the smartphone age, something born alongside front-facing cameras and high-speed internet. But Bell Labs had already built the future, and almost no one wanted it. The Picturephone required a special booth. It cost the equivalent of a luxury vacation per call. And there was a deeper resistance, harder to measure. People did not want to be seen while they spoke. They wanted to answer the phone in pajamas, unshaven, mid-meal. A camera intruded on that privacy in a way the public was not ready to forgive. At the 1964 World's Fair in New York, visitors stepped into booths and spoke face-to-face with strangers in Disneyland, 3,000 kilometers away. The technology worked, the demonstrations succeeded, and then, commercially, it failed almost completely. Bell offered the service in a handful of cities. Few subscribed. The lines were quietly shut down within a decade. What this reveals is that technological readiness and cultural readiness are not the same thing. A device can function perfectly and still arrive into a world that does not yet want what it offers. The Picturephone did not fail because it didn't work. It failed because the public's relationship with visibility, with being watched mid-conversation, had not yet shifted. That shift took 50 more years, a pandemic, and a generation raised on cameras pointed at their own faces. It is strange to consider that the resistance was never about the wires or the screens. It was about comfort with being seen, and that kind of comfort cannot be engineered. It has to be lived into slowly by an entire culture, one uncomfortable phone call at a time. Passive house design, a different kind of building, a different kind of patience. A house in Darmstadt, Germany, that uses almost no energy to heat itself, even in winter. Built in 1990, it looked, from the outside, entirely ordinary. The textbook story of sustainable architecture often begins recently, with solar panels on rooftops, with electric heat pumps, with a sense that climate-conscious building is a product of the last 15 years. But the gap in that story is the decade when passive house design was dismissed as academic excess. The insulation was thicker than builders thought reasonable. The windows were triple glazed and expensive. The air tightness required a level of construction precision that most contractors considered impractical, even unnecessary, for a planet that did not yet feel the urgency of changing its habits. Wolfgang Feist and Bo Adamson developed the standard through careful, unglamorous calculation. How much heat a human body releases, how much sunlight a south-facing window captures, how little energy a home needs if nothing is allowed to leak. The first house built to these specifications used roughly a tenth of the heating energy of a conventional one. For years, it remained a single example, visited by engineers, ignored by the broader construction industry. What this implies is that good ideas in architecture do not spread through proof alone. They spread through cost, through regulation, through decades of slow cultural pressure, before scale becomes possible. The physics behind passive house design were sound from the very first calculation. What took 30 years was not the discovery. It was permission, the moment when governments and homeowners finally agreed that the upfront cost was worth the silence of an exterior wall that never lets the cold in. A house that needed no apology for using almost nothing has become, eventually, the standard everyone is now asked to meet. Hiller flying platform, a man standing on it, and a sound like an enormous fan beneath his feet. The established view of military aviation in the 1950s held that the future belonged to faster jets, bigger wings, more altitude. But somewhere in that focus on speed, a smaller, stranger idea was dismissed almost on sight. The Hiller flying platform asked a soldier to simply stand upright on a disc, lean his body to steer, and hover a few meters above the ground. It looked, to the generals who watched it, like a toy. It offered no speed advantage. It carried no weapons. It seemed, on paper, almost pointless next to a helicopter. In 1955, Charles Zimmerman and engineers at Hiller Aircraft built and tested the platform in small demonstrations for the US military. It worked. A person with almost no training could stand on it and hover, lean forward, and travel slowly across open ground. But the project was shelved. The military wanted range, payload, armor. A platform that a man balanced on, exposed and slow, did not fit the era's appetite for power. What this leaves behind is a quiet lesson about timing and audience. The flying platform was not too difficult to build. It was simply asking the wrong question of the wrong era. Decades later, the same underlying principle, a human held aloft by ducted air, controlled by posture and balance rather than complex instruments, reappeared in hoverboards, in personal flight prototypes, in the quiet research labs, now chasing single-person aviation for entirely different reasons: convenience, sport, curiosity, rather than war. The platform asked a question the world was not yet curious enough to answer. Pneumatic Mail. The shape of the answer changed. The question somehow never went away. A tube buried beneath a city street, carrying a letter faster than any horse or wagon ever could. For decades, the textbook story of mail delivery moved in a straight line. Horse, then train, then truck, then airplane, each replacing the last entirely. But buried in that tidy progression is a system that ran underground, almost invisibly, for nearly a century. Pneumatic Mail used compressed air to push canisters through narrow tubes beneath the streets of Paris, London, New York, and Berlin. Engineers initially proposed it to skeptical city officials who saw mainly cost. Digging tunnels, maintaining pressure systems, all to move paper that a person could simply carry. In the 1860s, and again through the early 20th century, cities built these networks anyway, often starting small, connecting a handful of post offices before expanding into systems carrying hundreds of thousands of messages a day. In Paris, the tubes ran beneath the city for over 100 years, finally closing in 1984. New York's system, threading beneath Manhattan, moved mail at speeds that modern traffic still cannot consistently match. What survived this dismissal is more interesting than what disappeared. The system never scaled to replace trucks or trains for ordinary mail. But hospitals discovered something the postal services hadn't fully anticipated: a closed, fast, contamination-free way to move blood samples, lab results, and medication between departments. That narrower use case never went away. The lesson sitting quietly inside this history is that an idea dismissed as too expensive for its original purpose can survive by shrinking, by finding a smaller room where its advantages still matter. Pneumatic Mail did not fail. It simply found the one place left where speed under pressure was worth the cost of the tube. Beneath the floors of hospitals today, the same hiss of compressed air still carries something urgent from one room to another. Iron lung. A metal cylinder, the length of a person, with a head sticking out of one end, and a mirror angled so the patient could see the room behind them. The established narrative of medical technology tends to celebrate miniaturization. Devices getting smaller, more portable, more comfortable, generation after generation. But the iron lung does not fit neatly into that story, and so it has mostly been left out of it. It was loud. It was enormous. It required a patient to lie immobile for weeks, sometimes years, while the machine forced air in and out of paralyzed lungs. As soon as smaller positive pressure ventilators became available in the 1950s and 60s, the iron lung was retired quickly, almost gratefully, and rarely discussed again. During the polio epidemics of the early 20th century, before vaccines existed, the iron lung was the only thing standing between a paralyzed diaphragm and death. Philip Drinker and Louis Agassiz Shaw built the first version at Harvard in 1928. Hospitals scrambled to build more as outbreaks spread. Rows of iron lungs lined hospital wards, each one a person breathing only because a machine outside their body was breathing for them. What gets lost when a technology is replaced quickly is the memory of how much it mattered while it was the only option. A handful of polio survivors lived inside iron lungs for the rest of their lives, decades after the epidemic ended, because their muscles never recovered enough to breathe unassisted. Their machines, kept running long after the disease was controlled, became strange monuments, proof that the ugliest, least elegant solution can still be the one that saves a life when nothing smaller yet exists. A machine too large to love became, for a generation of frightened parents, the only sound of their child still breathing. The cochlear implant, a wire threaded surgically into the inner ear, carrying sound where sound could no longer travel naturally. For decades, the established medical view held that deafness caused by inner ear damage was permanent, that no device could substitute for the intricate hair cells nature had already lost. But that certainty rested on an assumption that had never been seriously tested with modern electronics. Early researchers who suggested otherwise were met with real skepticism from within their own field. Stimulating the auditory nerve directly, electronically, seemed to many specialists like a fantasy borrowed from science fiction, rather than a plausible medical intervention. In 1957, French researchers Journeau and Ariès placed an electrode on the auditory nerve of a deaf patient and produced a crude sensation of sound. It was not language. It was not music. It was closer to noise, an electrical hum the patient could at least detect. Decades of refinement followed. Graham Clark in Australia, William House in the United States, slowly turning that crude signal into something a brain could learn to interpret as speech. What this implies reaches beyond hearing itself. The cochlear implant proved something quietly profound, that the brain does not need a perfect biological signal to construct meaning. Given an imperfect electronic substitute, given enough time and enough exposure, the brain rewires itself to listen anew. Children implanted young can learn spoken language almost as if they had heard from birth. Adults relearn it more slowly, piecing meaning back together, one strange new sound at a time. The ear, it turns out, was never the only thing doing the listening. The mind was doing most of it all along. Smell-o-vision, a movie theatre suddenly filled with the smell of oranges, piped in through vents during a single scene in 1960. The textbook story of cinema technology celebrates sight and sound as the only senses worth engineering for. Better screens, better speakers, sharper colour. But for one strange experiment, a producer named Hans Lauber believed smell belonged in that list too, and the film industry's reaction was closer to ridicule than curiosity. Critics mocked the system before most of them had even experienced it properly, assuming it would be gimmicky, distracting, faintly absurd. Smell-o-vision debuted with a single film, Scent of Mystery, in 1960. Tubes beneath each seat released specific odours timed precisely to moments in the story. Pipe tobacco, coffee, oranges. The technical execution, however, lagged behind the ambition. Scents lingered too long, arrived too late, or didn't reach every seat evenly. Reviewers focused almost entirely on the malfunctions, and the format quietly disappeared after this single release. What survived was not the format itself, but the underlying instinct, resurfacing decades later under different names. Theme park attractions began experimenting with scent alongside motion and water spray. Theatres branded as 4D installed seats that shook, sprayed mist, and yes, occasionally released scent, synchronized far more precisely than 1960s tubing ever allowed. The idea was never wrong. It was simply executed with technology unequal to the ambition behind it. There is a particular kind of failure that isn't really failure at all. An idea released too early into hardware that cannot yet support it, waiting patiently for engineering to finally catch up to imagination. The nose remembers what the eye forgets. It only needed better tubing to prove it. Sony AIBO. Same era, a different kind of waiting. A small robotic dog, tilting its head toward a sound, blinking its mechanical eyes at the camera flash of curious onlookers. In a Tokyo electronics store, 1999. The established view of robotics in consumer markets held that machines belonged in factories, not living rooms. Useful, industrial, invisible, never meant to be loved. But Sony's engineers were quietly testing a different premise, and much of the public, along with most of the tech press, treated the idea as an expensive joke. $3,000 for a robot that fetched nothing, cleaned nothing, cooked nothing. It simply walked, reacted, and seemed, in some unsettling way, to recognize its owner. AIBO launched in Japan in 1999 and sold out within 20 minutes online. Each unit shipped with sensors that let it respond to touch, sound, and light, slowly developing what Sony called a personality, shaped by how its owner interacted with it over weeks and months. Critics called it a toy for people with too much disposable income. Few saw it as a meaningful step in robotics. Sony itself discontinued the line in 2006, a casualty of cost-cutting during a difficult financial period, and the project was treated by many as a closed chapter. What the dismissal missed was how much groundwork AIBO laid for an entire field that hadn't yet found its name: home robotics, emotional computing, machine companionship. All of it traces a line back to a small plastic dog learning to recognize a face. Years later, robotic vacuum cleaners, smart speakers with personality, and companion robots for elderly care all inherited, knowingly or not, lessons first tested on AIBO's sensors and its slowly developing behavioral code. It is easy to mistake a toy for something trivial. Sometimes, a toy is simply the only shape a serious idea is allowed to take before the world is ready to take it seriously. The dog never barked at anything real. It only taught the future to listen. Rocket mail. A rocket, packed with mail sacks instead of a warhead, launched from a small island off the coast of Germany in 1931. The textbook story of postal innovation rarely mentions rockets at all, focusing instead on planes, trains, and eventually digital communication that made physical delivery seem almost quaint. But for a strange decade, several countries genuinely experimented with rocket mail, and most observers considered the entire premise faintly ridiculous. A letter did not need to travel at the speed of an unguided explosive device. The risk of failure was high. The cost made no economic sense for anything but a handful of collectible stamps. Gerhard Zucker conducted some of the most publicized rocket mail tests in Germany, and later in Britain through the 1930s. Several launches failed outright, rockets exploding on the ground or veering wildly off course, sometimes injuring onlookers who had gathered to watch. Officials grew wary. Postal services largely refused to formally adopt the method, treating it as a novelty for philatelists rather than a viable delivery system. What endured was not the rocket itself, but the appetite it revealed, a willingness to imagine mail delivered at extraordinary speed, regardless of practicality. That appetite resurfaced decades later in research into suborbital cargo delivery, in modern companies experimenting with rocket-based package transport between continents in under an hour. The economics remain difficult even now. But the dream Zucker chased with scorched, half-functional rockets in a field in the 1930s is, in essence, the same dream funded today with considerably more capital and considerably better guidance systems. A failed letter, blown apart over a German field, somehow still arrived, decades late, at an idea worth keeping. Container shipping. A steel box, the size of a small room, lifted off a ship by crane in Newark, New Jersey in 1956. For decades, the established view of global trade assumed that loading and unloading cargo, piece by piece, sack by sack, crate by crate, was simply the unavoidable cost of moving goods across an ocean. But a trucking entrepreneur named Malcolm McLean looked at the hours dock workers spent manually loading loose cargo and saw not inevitability, but waste. Shipping executives, port authorities, and labor unions met his idea with open resistance. Standardizing cargo into uniform steel boxes meant rebuilding ports, redesigning ships, and eliminating thousands of dock worker jobs that depended on the old, inefficient system. McLean's first container ship, the Ideal X, sailed from New Jersey to Houston, carrying 58 containers in 1956. The cost of loading cargo this way dropped by a factor that stunned even McLean's own calculations. Handling costs per ton fell to a small fraction of what manual loading required. Ports resisted adopting the standard for years. Some labor unions fought it for over a decade, recognizing correctly that it would shrink their workforce. What followed was not a gradual shift, but an irreversible one. Once a handful of major ports adopted standardized containers, every port that refused became, almost overnight, uncompetitive. Goods could move from a factory in Asia to a shelf in Europe through a chain of trucks, trains, and ships, without ever being touched by human hands in between. Global manufacturing reorganized itself entirely around the existence of the box. A simple steel rectangle, resisted by nearly everyone with something to lose, quietly became the skeleton holding up the modern world's entire supply of everything. The 3-point seatbelt. A car crash test, filmed in black and white, where a dummy without a certain piece of webbing is hurled forward through a windshield. The established view in the automotive industry through the 1950s held that seatbelts, where they existed at all, were a minor accessory, a lap strap, uncomfortable, rarely worn, and only marginally protective in a serious collision. But a Swedish engineer named Niels Bolin had spent years working on ejector seats for aircraft, where the problem of securing a human body against violent force had already been solved with more rigor than the automotive industry had ever applied. When Volvo hired him in 1958 and asked him to improve on existing seatbelt designs, manufacturers across the industry showed limited interest. A car that looked safer, they worried, might imply that other cars were dangerous, an admission no one wanted to make in advertising. Bolin designed a belt that crossed both the chest and the lap in a single V shape, anchored at a single point near the hip. It took him roughly a year to refine the design into something that could be put on with one hand and would distribute crash force evenly across the body's strongest bones. Volvo introduced it as standard equipment in 1959. Crucially, Volvo also made the patent freely available to every competing manufacturer, refusing to profit exclusively from a design that could save lives elsewhere. What followed was slow, then sweeping. Country after country passed laws requiring seatbelt use, often against public grumbling about comfort and personal freedom. Estimates suggest the 3-point belt has saved over 1 million lives since its introduction, a number large enough to lose its emotional weight, reduced to a statistic recited in driving lessons. A single engineer, borrowing a solution from the sky, quietly rewired what survival looks like on the ground. Velcro, a burr from a plant, stuck stubbornly to a dog's fur after a walk through the Alps, examined under a microscope by a curious engineer in 1941. For decades, the established view of fastening, buttons, zippers, laces, buckles, felt complete, a closed category of solved problems requiring no further innovation. But Swiss engineer Georges de Mestral, picking burrs off his dog's coat, noticed something the rest of the world had simply stopped looking at closely. Tiny hooks on the burr's surface, catching on the fine loops of fur. When he proposed building a fastening system based on this mechanism, manufacturers were openly skeptical. A fabric covered in tiny hooks seemed impractical to mass produce, fragile, and faintly absurd as a replacement for something as simple and trusted as a button. De Mestral spent years refining the manufacturing process, eventually developing a way to weave nylon under infrared light to form durable hooks on one strip and soft loops on another. He patented the invention in 1955, naming it Velcro, a blend of the French words for velvet and hook. Early sales were slow. Fashion designers largely ignored it, and the textile industry treated it as a gimmick suited only to children's clothing or specialty gear. What changed its trajectory was an unlikely industry. NASA, designing equipment for use in zero gravity, needed fasteners that worked without fine motor precision, that held firmly under stress, that astronauts could manage even in thick gloves. Velcro fit perfectly. Its association with space travel gave it a credibility fashion alone never could. From there, it spread into shoes, medical devices, military gear, and eventually back into the everyday closets that had once dismissed it. A dog's afternoon walk through the mountains became, improbably, the reason millions of children now dress themselves without anyone tying a single knot. The microwave oven, a small box on a kitchen counter, humming quietly, having just melted a chocolate bar in an engineer's pocket without any flame or visible heat source. The established story of cooking technology through most of the 20th century assumed that heat had to come from outside the food, from a flame or a coil, slowly working its way inward. But radar engineer Percy Spencer, working for Raytheon in 1945, noticed something the rest of his field had overlooked entirely. Standing near a magnetron, a component used in radar systems, he felt the chocolate in his pocket begin to soften. Curious rather than alarmed, he tested the effect deliberately on popcorn kernels, then on an egg, which promptly exploded. Raytheon's leadership, when shown the early prototype, struggled to imagine ordinary households wanting a machine that cooked with invisible waves rather than visible fire. The first commercial microwave oven, released in 1947, stood nearly 6 feet tall and cost as much as a small car. It required water cooling and dedicated electrical wiring, making it impractical for any kitchen smaller than a restaurant's. Home cooks, when they encountered the idea at all, treated it with suspicion, distrustful of food prepared by something resembling the same technology used in military radar installations. It took roughly 2 more decades of miniaturization and falling costs before a countertop version became affordable for an ordinary household. Even then, adoption was gradual, driven less by marketing than by changing daily life. More households with 2 working parents, less time for slow meals, a growing comfort with convenience that earlier generations had resisted on principle. What sits quietly beneath this history is how often the most ordinary objects in a home began as something nobody asked for, built from a technology designed entirely for war, repurposed by accident, by a man with chocolate melting in his pocket. The radar that once searched the sky for enemy aircraft ended up simply warming dinner. Electric car. Electric vehicles are often seen as a modern invention created to address environmental concerns and reduce dependence on fossil fuels. However, their history goes back much further than many people realize. Long before gasoline-powered cars became dominant, electric vehicles were already competing for a place on the roads and were, for a time, among the most popular forms of motorized transportation. Imagine a city street in 1900. Horse-drawn carriages share the road with early automobiles, while electric cars move quietly through the traffic. Unlike gasoline vehicles, which were noisy and produced smoke and unpleasant odors, electric cars offered a smooth and silent driving experience. At the beginning of the 20th century, the future of transportation was still uncertain, and many people believed electric vehicles could become the standard choice for motorists. Electric cars had several advantages over their gasoline-powered rivals. They were easier to operate because they did not require manual engine cranking, a process that could be difficult and even dangerous. They were also cleaner, producing no exhaust emissions in city streets. Because of their simplicity and comfort, electric vehicles became especially popular in urban areas. At their peak, they accounted for roughly 1/3 of all automobiles in the United States. Advertisements often promoted them as convenient and elegant vehicles, suitable for everyday use. Despite their early success, electric vehicles faced significant challenges. The discovery of large oil reserves in Texas made gasoline cheaper and more widely available. Around the same time, the invention of the electric starter motor removed one of the biggest disadvantages of gasoline cars by eliminating the need for hand cranking. In addition, Henry Ford's assembly line production methods dramatically reduced the cost of gasoline-powered vehicles, making them affordable for a much larger number of consumers. Battery technology, however, did not advance at the same pace. Electric vehicles remained limited by short driving ranges and long charging times. As gasoline became increasingly inexpensive and convenient, consumers gradually turned away from electric cars. By the 1920s, they had almost disappeared from the market. For much of the 20th century, electric vehicles survived only as a historical footnote. Their return began decades later with advances in lithium-ion batteries, growing environmental awareness, and government regulations aimed at reducing emissions. Today, electric vehicles are once again becoming a major part of the automotive industry. The story of the electric car shows that technological progress is not always linear. Sometimes an idea can disappear for generations before returning when conditions finally allow it to succeed. Nickel-ion battery, another kind of patience, measured differently. A battery submerged in a glass jar of alkaline solution, still producing a steady current after being left untouched in a basement for over 60 years. The textbook story of battery technology generally follows a straight line towards smaller, lighter, more energy-dense cells, with little patience for anything bulky or old-fashioned. But Thomas Edison's nickel-iron battery, developed in the early 1900s, never competed well on the metrics that came to matter most to that story. It was heavy. It held less energy per kilogram than competing designs. Lead-acid batteries, cheaper to produce, quickly dominated the market for vehicles and industrial use, leaving Edison's design to be remembered, when it was remembered at all, as an over-engineered curiosity. Edison had designed the battery, hoping it would power early electric vehicles, investing years and a significant portion of his own fortune into refining its chemistry. Commercially, it underperformed against expectations. But the nickel-iron cell had one property almost no other battery of its era could match. It was nearly impossible to destroy through overcharging, deep discharging, or decades of neglect. Some original units, manufactured over a century ago, are still functioning today, having outlived the vehicles and the inventor who built them. What this longevity reveals is a quiet tension in how technology gets judged. The market rewards what is cheap and immediately convenient, not necessarily what lasts. Nickel-iron batteries found a second life in applications where durability mattered more than weight. Backup power systems, railway signaling, off-grid solar storage in remote locations, where a technician might not return for years. The battery that failed to win the market it was built for eventually found a much smaller, much quieter market, built entirely around what made it fail there in the first place. Some inventions are not ahead of their time or behind it. They are simply built for a kind of patience the world rarely thinks to ask for. Solar panels. Solar panels are now a familiar sight on homes, businesses, and large-scale power plants around the world. They are often presented as a key technology in the transition toward cleaner energy systems. Yet, for much of the 20th century, solar power was considered far too expensive to become a practical source of electricity for ordinary consumers. What is now a common feature of suburban rooftops once belonged almost exclusively to the world of space exploration. Imagine a single silicon panel in 1958, quietly converting sunlight into electricity. The technology worked, but at an extraordinary cost. Producing electricity from solar cells was so expensive that only a few specialized applications could justify using them. Among those applications were satellites, where reliability mattered far more than price. In orbit, there was no possibility of sending a technician to repair a failed power source, making solar cells an ideal solution despite their high cost. The foundations of modern solar technology were established in 1954 when Bell Labs developed the first practical silicon solar cell. Its efficiency was impressive for the era and demonstrated that sunlight could be converted directly into usable electricity. However, the technology remained economically impractical. The cost per watt was far beyond what households, businesses, or utility companies could afford. As a result, solar panels were produced in limited quantities and served mainly the aerospace and defense sectors. For the next several decades, solar power was viewed more as a promising future technology than an immediate energy solution. During the 1970s and 1980s, many engineers and policymakers supported continued research into solar energy, but few believed it could compete with conventional sources such as coal, oil, or natural gas in the near term. The main challenge was not the science behind solar power, but the cost of manufacturing the panels. Progress came gradually through countless improvements in production techniques. Demand from small-scale applications, including calculators, road signs, and remote monitoring equipment, helped expand manufacturing and lower costs. Each new use created opportunities for companies to refine production processes and increase efficiency. The most dramatic change occurred during the 2000s, when large-scale manufacturing expansion, particularly in China, transformed the economics of solar energy. Massive investments in production capacity reduced costs at an unprecedented rate. Compared with the earliest commercial solar cells, the price per watt fell by more than 100 times, making solar power affordable for homes and businesses across the world. The history of solar panels demonstrates an important lesson. Technological limitations are not always determined by physics. In many cases, the greatest obstacle is cost. Through decades of innovation, investment, and large-scale manufacturing, a technology once reserved for satellites in the vacuum of space eventually became a practical source of electricity for ordinary rooftops everywhere. Memory foam. Memory foam is now one of the most recognizable materials in the bedding industry, commonly associated with mattresses, pillows, and products designed to improve comfort during sleep. Millions of people use it every night without realizing that its origins lie not in the furniture industry, but in aerospace research. What began as an attempt to protect astronauts from extreme physical forces eventually became a technology focused on helping ordinary people rest more comfortably. Imagine pressing your hand into a block of foam and watching the imprint remain visible for several seconds before slowly disappearing. Unlike conventional foam, which immediately springs back into shape, memory foam responds gradually to pressure and heat. This unusual behavior allows it to conform closely to the body, distributing weight more evenly across its surface. Today, this characteristic is considered ideal for mattresses, but that was not the purpose for which the material was originally developed. In 1966, researchers working for NASA were searching for better cushioning materials capable of protecting astronauts during launch and re-entry. These phases of space travel expose the human body to intense forces, creating a need for materials that could absorb pressure effectively while maintaining support. Their work led to the development of a viscoelastic polyurethane foam, often referred to as temper foam. The material demonstrated an exceptional ability to distribute pressure evenly and absorb energy, making it well suited for aerospace applications. Despite its technical success, memory foam did not immediately become a commercial product. Manufacturing costs were high, and companies struggled to identify consumer markets that could justify its expense. For many years, the material remained largely unknown outside specialized industries. While researchers recognized its advantages, there was no obvious large-scale application capable of turning it into a mainstream product. During the 1980s, NASA made the technology available to the public, allowing private companies to explore potential uses. Some manufacturers began incorporating memory foam into medical products such as wheelchair cushions and hospital mattresses. These applications benefited from the material's ability to reduce pressure points and improve comfort for patients who spent long periods in bed or seated in wheelchairs. Even so, memory foam remained a niche material known primarily within healthcare settings. The breakthrough came during the 1990s when a Swedish company refined the formula and introduced memory foam mattresses to consumers. The same slow recovery property that helped protect astronauts from intense forces proved remarkably effective at supporting the human body during sleep. Consumers quickly embraced the material for its comfort and pressure-relieving qualities. The history of memory foam illustrates how innovations often find their greatest success in unexpected places. A material originally designed to withstand the demanding conditions of space travel ultimately found its most widespread purpose in the quiet comfort of bedrooms, helping people achieve better rest night after night. MRI Scanner. Magnetic resonance. Imaging, commonly known as MRI, is now considered one of the most important diagnostic tools in modern medicine. Hospitals around the world rely on MRI scanners to produce detailed images of organs, muscles, nerves, and the brain without the use of surgery or harmful radiation. Yet, when the technology was first proposed, many experts viewed it as an expensive and impractical idea. The path from a scientific curiosity to a standard medical instrument was far from straightforward. Imagine standing beside a massive cylindrical magnet, large enough to occupy much of a hospital room. The machine emits a constant hum while generating powerful magnetic fields capable of interacting with atoms inside the human body. In the early years of MRI development, some technicians and administrators worried about potential long-term effects that had not yet been fully studied. The technology seemed unfamiliar, complex, and intimidating compared with traditional medical imaging methods. For most of the 20th century, doctors depended primarily on X-rays and exploratory surgery to examine the inside of the body. While these techniques were valuable, they had significant limitations. X-rays were excellent for viewing bones, but far less effective for examining soft tissues such as muscles, ligaments, the brain, and internal organs. As a result, many medical conditions were difficult to diagnose accurately without invasive procedures. The scientific principles behind MRI were not originally developed for medicine. During the 1930s and 1940s, physicists studied the phenomenon of magnetic resonance as part of fundamental research into the behavior of atoms and molecules. At the time, few people imagined that these experiments would eventually transform healthcare. It was not until the 1970s that researchers, including Raymond Damadian and Paul Lauterbur, began exploring how magnetic resonance could be used to create images of the human body. Their ideas were met with skepticism. Building a full-body scanner required enormous magnets, sophisticated electronics, and substantial financial investment. Early MRI systems were extremely expensive and required specially designed facilities. Hospitals needed trained personnel capable of operating equipment unlike anything previously used in radiology departments. Many healthcare administrators questioned whether the benefits justified the cost. The turning point came as doctors began seeing the remarkable diagnostic capabilities of MRI. Unlike X-rays, MRI could reveal detailed images of soft tissues, detect early-stage tumors, identify spinal injuries, and uncover subtle abnormalities in the brain. Conditions that once remained hidden became visible with unprecedented clarity. As more hospitals adopted the technology, manufacturing costs gradually declined, and MRI scanners became increasingly accessible. Today, MRI is an essential part of modern healthcare. Its history demonstrates how discoveries made in basic scientific research can eventually produce life-changing medical innovations. What began as a phenomenon studied by physicists out of pure curiosity ultimately became a tool that helps millions of patients receive accurate diagnoses, guiding doctors toward answers when they are needed most. The automatic traffic light. The automatic traffic light is now one of the most ordinary and unnoticed parts of modern urban life. At almost every intersection in the world, colored signals quietly control the movement of vehicles and pedestrians, creating order in places where thousands of people and machines cross paths every day. Yet before these simple devices became standard, traffic management depended entirely on human effort, judgment, and physical presence. Imagine a busy city intersection in the early 20th century. A police officer stands on a small wooden platform in the middle of the street, using hand signals and a whistle to direct automobiles, streetcars, bicycles, and pedestrians. The officer must constantly observe the movement of traffic, make quick decisions, and maintain control over an increasingly complicated environment. For many city officials, this seemed like the only reliable solution. They believed that traffic required human judgment, and that no mechanical system could understand the unpredictable nature of a crowded intersection. However, the rapid growth of American cities began to challenge this assumption. As populations increased and automobile ownership expanded, the number of vehicles on urban roads grew beyond what police departments could effectively manage. Busy intersections became dangerous locations, with increasing collisions, delays, and risks for pedestrians. Despite these problems, early proposals for automated traffic signals were often met with skepticism. Many officials believed that machines operating on fixed schedules would fail because they could not react like a trained officer responding to changing conditions. The development of improved traffic signals gradually changed this perception. In 1923, inventor Garrett Morgan patented a traffic signal design that introduced an important innovation: a third position between stop and go. This warning phase allowed vehicles already in the intersection to clear before traffic moved in another direction, creating a safer transition. Earlier versions of automated signals had already appeared in some American cities, but widespread adoption remained slow because many communities were uncertain about replacing human control with mechanical systems. Over time, practicality became impossible to ignore. Automated traffic lights offered advantages that human operators could not consistently provide. They could function continuously, operate in all weather conditions, and manage traffic without requiring constant staffing. As cities expanded and the number of intersections increased, employing officers at every crossing became increasingly expensive and inefficient. By the middle of the 20th century, traffic lights had become a defining feature of urban infrastructure. What was once viewed as a cold and unreliable machine eventually became a symbol of organized city life. The transformation was not caused by a sudden technological breakthrough, but by a gradual realization that growing cities needed systems capable of handling problems beyond human capacity. The whistle, the hand signal, and the officer standing in the road slowly disappeared, replaced by a simple light that could patiently guide millions of journeys every day. The vacuum flask. The vacuum flask, commonly known today as a thermos, is one of the simplest and most familiar household objects. It keeps coffee warm, water cold, and drinks at the desired temperature for hours. Yet, its origins had nothing to do with kitchens, travel, or daily convenience. The technology behind it was created in a scientific laboratory, designed for experiments involving some of the coldest temperatures humans could produce. Imagine a carefully constructed glass container with two walls separated by an empty space. Inside this double-walled flask, a vacuum prevents heat from moving easily between the liquid and the outside environment. This simple but powerful idea allowed scientists to preserve extremely cold substances for much longer periods than traditional containers could manage. In the late 19th century, such a device represented a major achievement in experimental physics. The vacuum flask was first developed in 1892 by Scottish physicist James Dewar during his research into cryogenics, the study of extremely low temperatures. Dewar needed a reliable method for storing liquefied gases, such as liquid hydrogen, which could quickly warm and evaporate when exposed to surrounding heat. His solution was a specially designed container that minimized heat transfer through insulation created by a vacuum layer. At the time, the invention was considered scientific equipment rather than a commercial opportunity. Dewar did not patent the design, as he viewed it primarily as a tool for laboratory research. He was interested in advancing physics, not creating a consumer product. As a result, the idea remained largely within scientific circles until others recognized its broader potential. Two German glassmakers, Reinhold Berger and Albert Aschenbrenner, saw an opportunity beyond the laboratory. They realized that the same vacuum insulation that protected liquid gases from heat could also preserve everyday liquids at stable temperatures. By improving the durability and practicality of the design, they created a version suitable for general use and patented their improvements in 1903. They later introduced the name Thermos, derived from a Greek word associated with heat. However, convincing the public of the technology's value was not immediately easy. The idea that one container could keep hot drinks hot and cold drinks cold seemed almost unnatural to many people. Early marketing efforts focused on explaining how vacuum insulation worked. Public confidence grew when explorers, travelers, and soldiers began using vacuum flasks in harsh environments, where their reliability became impossible to ignore. Over time, the laboratory instrument became a household essential, a device created to help scientists study extreme cold eventually found its place in everyday life, quietly keeping millions of cups of coffee warm and drinks cool. The vacuum flask remains a reminder that some of the most ordinary objects around us began as solutions to extraordinary scientific challenges.